Okay. All right. So up until now, we've sort of talked about the basic idea of what symplectic manifolds are, talked a little bit about sort of their structure, in particular their local structure, how you can compare different symplectic manifolds, symplectic structures on the same manifold. And we've introduced one really important big source of symplectic manifolds, which is scalar manifolds. So in particular, smooth, projective, or affine varieties over the complex numbers. All right, well, that's a pretty good supply of them. Now, why do we care if a manifold is symplectic? What can we do with a symplectic manifold? And one really important answer is one I kind of discussed a little bit at the start of the class, which is in classical mechanics, sort of one way of formulating classical mechanics is to write everything in terms of phase space that measures the different states your physical system can be in, and think about time evolution as a flow on that phase space. And the way we describe that flow is through symplectic geometry, through what are called Hamilton's equations. So I want to sort of, I went through that a little bit at the beginning of the course, but I wanted to kind of take that idea and, as mathematicians always do, kind of take that kernel of interesting stuff and kind of abstract away to what's happening there. So I don't expect you to remember the details of what happened in my discussion of classical mechanics at the start of the course, but the operation that we use is what's called Hamiltonian vector fields. So if I have a function on a symplectic manifold, and in classical mechanics, this would be the function of total energy, kinetic plus positive energy, which is often called the Hamiltonian function, and thus called H. But this example, it doesn't have to have anything to do with classical mechanics, just any symplectic manifold, any function from it to the real numbers. There's a unique vector field that satisfies the equation of you take the differential of your function, so that gives you a one form, and there's a unique vector field which contracted with the symplectic form gives you that one form. So just to kind of emphasize what this means algebraically, this means that when I contract xh against any vector field, let me call it y, that gets me a function, and it should be the same function as taking the directional derivative with respect to y of h. So there's a unique vector field xh that satisfies this equation. And that's called the Hamiltonian vector field of the function h. And as I say, h is called the Hamiltonian function. In physics, that would really mean like the energy function on your space of states. Here, I just mean the function that I'm using to get a Hamiltonian vector field. All right, so this is taking the Hamiltonian formulation of classical mechanics and abstracting it away to just say, oh, I could have any symplectic manifold, any function, and I would get a vector field out of this. And of course, that vector field generates a flow. And that flow is the time evolution on your phase space. Just, that's physics, right? Like the whole question of physics is, I have my world, it's in this state. What state is it going to be in 1 second, 2 seconds, 3 seconds, etc. Right? And you find that by taking this Hamiltonian vector field and integrating it to a flow. So just a basic example. If we have a single particle in Rn and no potential energy, no forces acting on it, you'll sometimes hear this called like a free particle, then the phase space is T star Rn with the coordinates along the base giving us position and the coordinates in the fiber giving us momentum. So you'll note this time I was careful, I screwed this up earlier, but Q is the position and P is the momentum, even though position starts with a P. Say that. So in this case, the Hamiltonian is just the kinetic energy. And that's, well, since I'm writing things in terms of momentum, I have to square the momentum and divide by 1/2 times the mass. So remember, you might be more used to kinetic energy being 1/2 mv squared, and I have to use that mv as p. Okay, and I write that as the dot product of the momentum itself. All right, the differential of that is 1/m times pi dpi. And so when I turn that into a Hamiltonian vector field using the symplectic form, right, I have to have a vector field such that when it eats the symplectic form, the one form it spits out is, the sum of pi dpi. And that's 1/m times pi ddqi, right? So because the di and the qi are kind of dual coordinates under the symplectic form, I swap a dpi for a ddqi. All right. So if I integrate that to a flow, I find that if I start at qpt, indeed, after time t, I'm at q plus p times t over m, comma p. So the momentum stays the same, and I travel in the direction that the momentum vector points at a speed, which comes from the momentum vector via this formula p equals mv. All right, so this is very easy from a physical perspective, but it's sort of, everything in Hamilton's equations checks out when you do it this way. And one thing worth noting, momentum is conserved. All right, the momentum stays the same all the time, and you just move around according to your position. That'll come back later. I wanted to do one other tiny bit less trivial example. Still pretty easy, but a little bit more complicated. So another example to consider is the harmonic oscillator. And I could do this in higher dimensions, but it would just make life more complicated than it needs to be. Just kind of notationally, it's a little unpleasant. So I'm just doing this for a particle in one dimension. So you should think of this as like a particle on a spring where the spring is attached to the origin. So I have my kinetic energy term, 1/m(p squared), and I have my potential energy term. So as I go away from the origin in either direction, my potential energy increases, right? Because the spring is trying to pull me back toward the origin. All right, so when I compute this k/2, that's a constant that measures how strong is the spring, how hard does the spring pull back when I go away from the origin. So when I take the differential, I get 1/m pdp plus k q dq. And now I have a term q dq here. And the Hamiltonian vector field is, go away, 1/m p dq minus k times q ddp. So basically what's happening, right, what this term tells you in sort of physical terms is as you go away from the origin, the spring pulls you back towards the origin and your momentum is gradually getting sapped away. right? So this is telling you your momentum is decreasing, and it's decreasing in linear proportion to your distance from the origin, right? Q is the distance from the origin, is your position. So you're getting pushed back in the direction of the origin, and the further you get away, the stronger it's pulling. Okay, that's right. That's Newton's law. All right, if you want to actually solve this, it's sort of useful to write out what this actually says as a system of differential equations, right? It says that I'm writing Q dot for dq dt, because it's just kind of a pain in the butt to write dq dt all the time. So Q dot is 1 over m times p, P dot is minus k times q. And so the second derivative of q is equal to minus k over n. So this is this usual solution to the harmonic oscillator that you get sine and cos with some funny constants thrown in. And then depending on the initial conditions, you multiply the whole thing by a scalar that gives you the amplitude. And you also have a phase angle. And the kind of picture here in phase space, right, is that here's your q direction, here's your p direction, and you're going to make an ellipse in this space. And the ratio between q and m sort of determines, the product of q and m determines how fat or thin this ellipse is. The ratio between k and m tells you how fast you go around the ellipse, in particular which way you go around it. And then the amplitude tells you sort of how much energy did you start with, right? So this path here, this is actually a level set for the Hamiltonian function. We'll see in a moment why that's the case, but if you know little basic physics, you know that energy should be conserved. So you should be moving around on a level set of the energy function, which in this case is a one-dimensional submanifold. So the question is just kind of how do you parameterize that one-dimensional submanifold? All right, any questions?
Sorry, what was the energy function here? Was that the Hamiltonian?
Yes, the Hamiltonian, right.
Okay.
Right, the Hamiltonian stays constant. I mean, it's essentially like conservation of energy is like, the statement that you stay on a level set of the energy function. We'll see mathematically why that happens in a moment. Oh yeah, there it is. Right. So this is a general fact about Hamiltonian vector fields. So if you want to know how the function h changes along trajectories of the Hamiltonian vector field, you should compute the directional derivative of h with respect to xh. And what's that? Oh, well, that's contracting xh with the differential of h. That's the definition of dh as a one form. And then when you say, oh, but wait a second, dh is the same as the symplectic form contracted with xh, you get that this is actually just taking the symplectic form and applying it to xh. So by the anti-symmetry of the symplectic form, you get 0. And conservation of energy comes out. So conservation of energy is really the fact that the symplectic form is anti-symmetric. There's sort of several of these little computations you do where You play around with these formulas we've already covered, Cartan's magic formula, etc., and out pops sort of basic facts about physics. So another thing you might want to consider is, well, what happens when I do this flow of a Hamiltonian vector field, sometimes called a Hamiltonian flow? Does the symplectic form change when I pull it back by that flow? And the answer is no. So if I want to see how the symplectic form is changing, I take its derivative with respect to the vector field. I take the Lie derivative of omega with respect to xh, and I use Cartan's magic formula. That's xh contracted with d omega, 0 because the symplectic form is closed. And on the other hand, the other term in Cartan's magic formula is d of the contraction of xh with, oh, there's an extra d there, sorry, with omega, which by definition is dh. So I'm taking d squared of h, that's 0. Right? So you'll note here, right, this derivative being 0, I'm kind of using two things. I'm using that the symplectic form is closed. That's key. So if you put in a non-closed 2 form, well, you can define, that's non-degenerate, an almost symplectic form. You can define the Hamiltonian vector field, but it won't leave the form alone. It'll move it around and change it, which that's not very physical. And then the kind of other term comes from the fact that d squared is 0. So the fact that the form, the one form I'm putting in, dh, is closed itself. And I kind of interpret this as saying that the kind of underlying physics doesn't change with respect to time. So like I said, you know, at least one way I like to think about this is the metric doesn't appear, right? I mean, like usually you would think of physics as depending on distances between things, but actually the metric of Rn doesn't make any appearance here. You only need to know the symplectic structure and the cotangent bundle. And if you do some coordinate change on Rn, you'll do a canceling coordinate change in the fiber direction to keep the symplectic form the same. So it's kind of the only thing that's controlling the underlying physics that you need to know to find time evolution is the symplectic form, and that won't change over time. So this sort of tells you why, if you're going to kind of do physics this way, you have to put in a closed 2 form, not just a random non-degenerate one. All right. If you run this equation backwards, it tells us something interesting. So what if we took a vector field that we had, then when we take the Lie derivative of the symplectic form for that, we get d of the contraction of the symplectic form with x. So we get that the symplectic form stays unchanged if and only if this contraction is closed. And when this happens, we call x a symplectic vector field. It's called symplectic because its flow is a symplectomorphism. Now, on the other hand, a vector field is going to be Hamiltonian if this contraction is exact. Maybe I will actually write that since it's an important observation. On the other hand, x is Hamiltonian if this contraction is exact. So exact forms are closed, but not all closed forms have to be exact. So every Hamiltonian vector field is symplectic. It leaves the symplectic form unchanged. But You can, if you are on a manifold that has non-zero de Rham H1, then there is a closed form which is not exact, and you can cook up a vector field whose pairing with the symplectic form will be that one form. And that will be a vector field which is symplectic, but not Hamiltonian. On the other hand, if the de Rham cohomology in degree 1 vanishes, then all closed forms are exact, so every symplectic vector field is Hamiltonian. Cool. Right. So let's talk about a few examples. One example which is contained in the book, but is always nice to have. I was surprisingly bad at drawing this. There's a vector field on the sphere, which is the derivative of rotation around an axis. So what I was trying to draw here, and did a relatively mediocre job doing, is I put an axis down the middle of the sphere. I look at the sphere rotating there, that's a flow on the sphere. So taking its derivative, I get a vector field, which I would call dd theta. Right? And in an earlier homework, you had to show that the symplectic form on the sphere is d theta wedge dh. And from that, you can read off that dd theta is the Hamiltonian vector field of the height function. So Hamiltonian vector fields, they're kind of weird. They have this property that, like, you have some function, you kind of, right, you're more used to thinking about like gradients of functions where you point in a direction where the function changes the most, but that's not what you want here. You want something which keeps the function constant. So rotation indeed preserves the height function. So it's at least plausible that height is the Hamiltonian function. No, this is something that's kind of doesn't have an obvious physical interpretation, right? There are physical systems out there, which are the S2 with this symplectic form, but they're not like something that's super easy to come up with, like a point moving around on a line. So I'm sure we'll see one of those eventually. Might be a little while, but if you can imagine such a physical system with the height being the energy, this is telling you you'll rotate at the same speed. Your time evolution will just be rotating the sphere with constant speed. All right. On the other hand of a symplectic vector field, which is not Hamiltonian. So I want to look at the 2 torus, and I want to think of that as the quotient of R2 by the subgroup Z2 of vectors with integer entries. So kind of the usual picture you'll see is you take the unit square and you glue this side to this side because the difference between them is an integer valued vector, and you glue this side to this side. And when you wrap that all up, you get the usual sort of donut picture, which I swear I know how to draw. There we go. But in terms of like coordinates and such, it's kind of easier to think about R2 mod Z2. So note here, there isn't a global coordinate X or a global coordinate Y, but they're perfectly good one forms dx and dy, because dx and dy are pull back to themselves under addition by any vector, in particular under an integer value. So on T2, there are well-defined one forms dx, dy, and a well-defined symplectic form, which is dx wedge dy. All right, excuse me. Now, when I take ddx, it's a perfectly good vector field that just points to the right, and I contract that with the symplectic form, I get dy. That's closed because d squared of y is 0, but it's not exact despite what the name looks like. On the torus, dy is not exact because y isn't a well-defined global function on the torus. If you want to really carefully think about this, you have a closed curve from any vertical line going from the bottom of that unit square to the top. And when you integrate the one form over that closed curve, you get 1. So I call this curve C, then the integral over C of dy is 1. If I have a non-zero integral over a closed curve, it can't be exact. All right, cool. By Stokes theorem. So this tells me the corresponding vector field, ddx, is symplectic, but not Hamiltonian. And I'll just mention in d equals 2, I can actually kind of picture what's going on, right? So if you think through what this operation of contracting with the symplectic form does, you're kind of hopefully you're kind of used to thinking of both one forms and vector fields as vectors secretly. And this operation is just rotation to the right by 90 degrees, depending on your orientation. So you can actually think about what it means to take a vector field and integrate over a curve the one form where you contract with the symplectic form. It's actually the flux of the vector field through that curve. So rather than kind of integrating along the direction that's parallel to the curve, you integrate along the direction that's perp to the curve. And of course, you need an orientation to make sense of that. And so the other way to think about why this vector field ddx isn't Hamiltonian, even though it's symplectic, is when I look at the flux through this curve, well, it's quite large, right? It's definitely not 0 because you're always pointing in the same direction. Unfortunately, I don't think there's as nice a picture in higher dimensions of what the heck this means. You know, there is some interpretation, but there's nothing quite so clean. All right. Any questions?
Yes, I have a question.
Mm-hmm.
I wasn't sure when you say flux through the curve, I don't actually know what that means. So can you, I mean, I think you said it in words, but I kind of, it didn't like quite sink in fast enough.
Okay. So let me just sort of say this very briefly. You know, actually on any two manifold, right, given a symplectic form, I can choose a compatible complex structure J and thus get a metric G, right? And by definition, G of UV is equal to omega of U JV. Right, so if I use the metric to identify one forms in vector fields, which is something you're kind of used to doing from vector calculus, then, you know, what should probably actually give this a name. you know, in the usual kind of tensor notation, this would be raising and lowering indices. But maybe just for kind of clarity, I'll give this a name, delta. So yeah, I'm doing this on the fly, so I'm sort of thinking, let me say that delta of one form is one form alpha gets sent to a vector field delta alpha. Okay. So in this case, right, I want to solve the equation that the symplectic form eating xhy is equal to the pairing between d, h, and y. Okay. Well, on the other hand, this is g of vxhy. And so what I'm finding here is that xh is minus j times alpha of dh. And I apologize if I screwed up the sign somewhere in there. That's certainly a realistic possibility. But you know, somehow the point is, if I use my metric to identify vectors in one forms, then the Hamiltonian vector field is take dh, think of it as a one form, think of it as a vector field, rotate that vector field using the complex structure.
I think the alpha in there is intended to be a delta, given the notation.
Oh, delta, yes, I'm sorry. Right, so, you know, what does it mean to do a line integral of some vector field contracted with the symplectic form over a curve, right? Well, now do this backwards. This means that I take my vector field, you know, apply the complex rotation to it, turn it back into a one form, and then integrate that. I think that's right. Anyway, so it's doing a usual line integral over your vector field rotated by 90 degrees using the complex structure to tell you which way you should rotate 90 degrees. And then, you know, like if you go take a vector calculus course, they might tell you about like having a codimension 1 surface in Rn. You can compute the flux through that by finding a unit normal to the surface, dotting your vector field with that, and then integrating over the surface. And you know, that's what's happening on a curve in 2 dimensions here. So if I take the normalized velocity, you know, if I parameterize my curve at unit speed, then I'll have a unit length velocity vector. And what I'll be doing to get a unit normal is using the complex structure to turn it to the right 90 degrees. And I'll be taking the dot product with that guy instead of the dot product with the velocity vector.
Just to make sure I understand, if you integrate the that flux that you discussed and you get something non-zero, then your vector field could not have been Hamiltonian,
Right.
Right. But just because it's 0 over one curve doesn't imply that it's Hamiltonian, right?
No, but if it's on a surface, right? I mean, a one form is exact if and only if it's integral around every closed curve is 0.
Right. So if you tested every curve, then the flux was 0.
Every curve, then yeah.
Gotcha. Thanks.
All right. So there's sort of, as I said, there's kind of a parade of these cute little calculations that tell you kind of interesting stuff about how things change along Hamiltonian vector fields. So another kind of important one, if you think about physics, is you have some function on your phase space. In physics, this is often called an observable. Observable. So it's some numerical quantity you can get out of your physical system. So function on phase space. Well, natural question is, how does this function change as we do time evolution? And of course, taking the derivative, we're going to get a Lie derivative with respect to the vector field. And so this is telling us there's sort of another way to write this. If I take a function and I take its Lie derivative with respect to any vector field, doesn't have to be symplectic, doesn't have to be Hamiltonian. Well, that's the same as contracting that vector field with df. And that's the same as hitting xfx as with the symplectic form. So if you kind of take this transformation from f into the Hamiltonian as granted, the Hamiltonian vector field as granted, computing how f changes over different vector fields is the same as computing what the symplectic form is between the Hamiltonian vector field and whatever vector field you're varying things with. So in particular, if my x is also a Hamiltonian vector field, then f is conserved. It doesn't change over time if and only if these guys are perp under the symplectic form. If xf and xh are perp symplectic form. So you can kind of translate any question about the function f into a statement about the Hamiltonian vector field instead. All right, well, this function where I take the symplectic form applied to xf, xg, that's a very important function. And it's so special, it gets its own name. It's called the Poisson bracket of f and g. So for our purposes, this is going to be our definition of the Poisson bracket. I turn f into a Hamiltonian vector field. I turn g into a Hamiltonian vector field. And then I put them into the symplectic form. Now, maybe it's just worth mentioning here. This is a little confusing because the construction of xf and the construction of xg depend on the symplectic form. So I'm really using the symplectic form 3 times here, right? And in particular, I'm using the fact that the symplectic form induces an isomorphism from the tangent space to the cotangent space. And I'll just mention, we'll come back to this later, I could kind of turn this around and get a bilinear form on not the tangent space, but on the cotangent space. In which case I would just be taking df and dg and putting those into that kind of inverse bilinear form. But we haven't gone through the linear algebra to actually sort that out. All right, so this is going to be a slightly involved calculation. I need to kind of motivate it a little bit, but I think it's a natural question. Well, I put in two functions. I do this operation that involves taking their Hamiltonian vector field, and I get out a new function. Well, this whole lecture is about whenever you have a function, try whacking it with this operation of turning it into a Hamiltonian vector field. So what is the Hamiltonian vector field of the Poisson bracket of f and g? And part of the reason it needs a little motivation is we're gonna have to have a new formula, which I'll try to explain. But maybe before that, I will stop for a moment, let people pause. I'm sorry, I wasn't looking carefully at the chat. It's a question, do we require H to be continuous or smooth? Yeah, continuous, as Paul says, continuous isn't good enough because continuous functions don't have differentials. For my purposes, I would just say smooth. You can get a well-defined one form from any function which is differentiable. Essentially, being differentiable as a function on a manifold means it has a well-defined differential as a one form. But then you have to ask, is that one form continuous, differential, etc. So I'm going to assume smooth just to make my life easier. You probably could weaken this a little bit. Are there any other questions?
Would that be at around the same time? Or maybe somehow.
I don't know. Yeah, probably I would see if Justin's able to do it. So it would might depend on his schedule. All right, great. Are there any other questions people thought of while we were having our break? All right. So indeed, let's come back to this question. I take this Poisson bracket. This is a way of starting with a symplectic form in two functions and getting a new function. So its Hamiltonian vector field should be something natural, right? It should have some reasonable description. Well, to find it, what we should do, we should take this function symplectic form applied to xf and xg, and we should take d of that. I can rewrite this symplectic form of xf, xg as the exterior derivative of the contraction with xg of the contraction with xf of omega. And I'll just mention here, because it's real easy to make sign errors when working with this stuff. Contraction always means you put that vector in the first entry, right? So if I want the symplectic form of xf, xg, I have to contract with xf first and then contract with xg. All right, cool. So I have d of this contraction. Well, I only know one formula for how exterior derivatives and contraction with vector fields commute past each other, which is Cartan's magic formula. So I do Cartan's magic formula to turn this d contraction with xg into a Lie derivative with respect to xg minus those things in the opposite order. Contraction with xg, d of contraction with xf of omega. That second term becomes 0 because the contraction of xf with omega is df. So this is contraction of xg with d squared of f, so that's 0. So good, I got rid of one term there, but now I have this term Lie derivative with respect to xg, contraction with respect to xf. And unfortunately, we don't have, have any formulas that tell us how to commute a Lie derivative past a contraction. So that's a new formula we need. It turns out it's not too bad, but I wanted to kind of explain this because all of these formulas, they just kind of, if you don't think about them geometrically, they just kind of float around and it's like, oh, okay, well, I guess that's true. I don't know why. So we'd like to think about what happens when you try to commute Lie derivative past contraction. So what I've always sort of said is you should think about these equations on forms in terms of integrating them against things, right? Forms, sort of by definition, are things you integrate. And well, as it happens, this is a one form. The formula I'm going to tell you is valid for all degrees, but this is a one form. So let's talk about it in that case. So I want to integrate it against some path. Well, so this is sort of useful to think about, like how do I think about Lie derivative and how do I think about contraction in terms of integrating against a cycle? And the way I think about contraction is I take my vector field, that generates a flow, and I can look at my cycle and let it trace out a surface under that flow. So I start with a cycle C, and then as I do some flow, I trace out a surface. And I was calling this S epsilon. So contraction is I look at my integral of my form omega over now this surface. I can integrate two forms over surfaces. And then I think about, okay, as I send the time that I evolved by to 0, my surface gets skinnier and skinnier and skinnier. And in fact, the integral along it is going to get closer and closer to being proportional to epsilon. So I divide by epsilon. So it's the derivative of the integral over that surface with respect to time as I evolve the surface for longer and thus get a bigger integral. So it's kind of capturing, how I also incorporate in the direction that my vector field pushes me off. Now, on the other hand, the Lie derivative is just how does the form itself vary? So with the Lie derivative, I look at here's C, I can get myself enough space. Here's its image under time evolution. And what's the difference between these? And again, what's the derivative of the difference between these integrals as I make the time that I pushed out sort of closer and closer to 0? So I hope this at least lets you see the difference here. In particular, Lie derivative, if I'm thinking of a curve, Lie derivative is an operation on one forms, where I look at two different curves and compare the integrals over those. Whereas contraction is something about integrating over a surface, which is why it involves decreasing the degree. So the question is, how do these interact when I do them in the two possible orders? Right, so doing contraction first and then Lie derivative means I trace out my surface with respect to one vector field, xf, and then I translate it with respect to xg. And I look at how the derivative, both as the surface gets further away from this other one, and as I thicken it. It's a It involves two derivatives. On the other hand, if I do them in the opposite order, that means I just evolve with respect to xg first, and then I trace out the surface with respect to xf. So, I mean, I tried to actually write everything out in terms of notation, but I think that might just make life worse. The kind of important thing to think about is one vector field gives you a surface, and the other one gives you some gap between the surfaces, and you're looking at the difference between the values on those. So the question is, how are the surfaces involved different? Well, there's one where I just sort of start with my original curve, and I evolve with respect to xf. And then there's two that play a different role. I can either take this guy S epsilon and evolve it with respect to xg, or I can first evolve the curve with respect to xg and then push off the curve with respect to xf. And those will be the different surfaces, because flowing with respect to xg and then with respect to xf is different from flowing with respect to xf and then with xg. And there's an operation in differential geometry which exactly measures the difference between doing those two things. When you have a vector field, I think I'm kind of contractually obligated to draw this picture, right? If you sort of have a vector field where here's one integral curve, here's another one, and if you do them in the opposite order, this parallelogram doesn't quite close up. The thing that kind of fills this in is the Lie bracket. So the Lie bracket of two vector fields exactly measures how their flows fail to commute. And so the Lie bracket is, you know, as I shorten the time that I've evolved for with respect to both of these guys, kind of what's the difference between these two surfaces up on the top. And the Lie bracket of xf and xg will exactly point between the two surfaces. Another way to say this is sort of the third side. So here I have these two surfaces coming off C. And of course, they're getting very, very small. Everything's happening very close to C here, but there's still some difference between them. And sort of closing off the third side is done via using the surface swept out by the Lie derivative. The Lie bracket of those two vector fields. Okay, if you go through this and do everything carefully, think about what it means in terms of forms. What this tells you is contraction of the symplectic form with the Lie derivative, that corresponds to sort of the third side here, is equal to Lie derivative with respect to xg, contraction with respect to xf, minus contraction with respect to xf, Lie derivative with respect to xg. Kind of the other way to see that this is true is, to sort of check that everything respects wedge product and gives you the right answer on exact one forms and on functions. So I won't write that out because I don't have it prepared. But there's also kind of an algebraic way of thinking about this, that you only need to check this on Rn, and every one form on Rn can be written out explicitly in terms of wedges of coordinates, and then you just write everything out and you check that all the coefficients match. So I was sort of trying to explain this geometrically, because if you just kind of write out all the algebra and you see the coefficients match, it doesn't tell you anything. you haven't learned anything at the end of the day. So somehow the important thing here is this story about like Lie bracket shows up exactly when you have two vector fields and you do some operation with them in the two opposite orders and look at the difference. Okay, so I can go back up to this equation that d of the symplectic form applied to Fg is the Lie bracket with respect to Xg, applied to the contraction with respect to Xf. Okay. And so this line is just recopied from up above. And now I apply this formula. So I can swap these terms of doing contraction with respect to Xf and doing Lie derivative with respect to Xg, but at the cost of adding on a term, which is the contraction against the Lie bracket of Xg and Xf. And you have to be really careful about signs here. I don't think I've screwed them up, but you just have to check against Canis de Silva and see what happens at the end. Well, this term here, this involves taking the Lie derivative of the symplectic form with respect to a Hamiltonian vector field, and that's 0. So that term goes away, and I just have the contraction of the symplectic form against this Lie bracket. And you'll note here, G and F are showing up in the opposite order they did in the symplectic form. So I'm going to swap them and get minus contraction with the Lie bracket of Xf and Xg. So there's a bunch of annoying stuff about what order things come in here. Suspect this is one of these things where, two different branches of mathematics, people made two different conventions, and we've all had to suffer since. So what we found is the Hamiltonian vector field of this function symplectic form applied to Xf, Fg is the Lie bracket of Xg, Xf, or written a bit differently because Lie bracket is anti-symmetric. Oops, that didn't work very well. Let me actually get myself room. This is the same as minus the Lie bracket of Xf, Xg.
Oh, quick question.
Mm-hmm.
I think I'm confused by something a little stupid, but you write right up there, you say it says d omega of Xf Xg. Why is that not always 0? Isn't d omega always 0? What am I missing?
Because it's d of this function.
Yeah, right. And that's not the same. Oh. Okay.
Right? So
Okay.
d omega applied to those vector fields, that doesn't make any sense. That's not even like a sensible expression.
Right. Okay, got it. Thanks. Yeah.
Mm-hmm. No problem. I appreciate the chance to clarify. Yeah, I mean, right, exactly what this whole proof lives on is exactly the fact that exterior derivative doesn't just commute past contraction like that. That's exactly what Cartan's magic formula tells you. Right? So it's exactly here I said, oh, well, yeah, I want to use the fact that D is closed, and there's sort of a contribution to this exterior derivative from D of omega, but there are also some correction terms that have to do with, well, wait, how does D commute past contraction? And here we see, okay, yeah, I mean, right, well, this calculation used that d omega was 0. The fact that I used d omega 0 and the fact that I already computed that symplectic vector fields keep this guy preserved. All right. Cool. Yeah, this calculation already involved using Cartan's magic formula, which incorporated d omega being 0. Okay, great. And I'll just mention, so I did this calculation with Hamiltonian vector fields, but actually it still applies to symplectic vector fields. If I have two symplectic vector fields, then their Lie bracket is Hamiltonian, and the function is gotten by putting the vector fields into the symplectic form, which again gives you a function. So I mean, Canis de Silva proves this in this generality. So I won't go through the proof again. You just note, oh, actually, if every equation here only used the fact that f and g were, the xg and xf were symplectic, not that they were Hamiltonian. All right. So Lie bracket, since I've mentioned Lie bracket, I'm now contractually obligated to define Lie algebras. Hopefully most people here have seen this definition at some point, but if you haven't, here it is. Lie algebra is a vector space equipped with a bilinear map, usually called a Lie bracket, which is antisymmetric. So the bracket of x and y is minus y of x, and it satisfies the Jacobi identity. There are various ways of writing this. I think this is one of these things where when you first encounter it, it always seems kind of awful. But this is basically the replacement for associativity. The kind of easiest way to remember it is that any expression where you take the bracket of two things and then bracket it with a third in any way you want, if you take x, y, and z and then their cyclic permutations, those will add up to 0. So there are other ways of writing this that emphasize other ways of thinking about it, but this is kind of the easiest one to remember, which is just like take sums over cyclic permutations and you will get 0. And the kind of, some people might dispute this with me. I would say like the kind of prime example of a Lie algebra is the vector fields on a manifold. So those have a Lie bracket that comes from Lie derivative. So I can write xy. Probably going to screw this up. I think I want to take the Lie derivative of, with respect to x of y. I didn't carefully check this before class. So, and there is this very annoying thing of somewhere you have to break some symmetry, right? So the Lie derivative of with respect to x of y is minus the Lie derivative with respect to y of x. So in choosing like which one of those you mean is the Lie bracket, there's some sign that shows up. And exactly this, well, why did we get that when I take the Lie bracket of x and y, that's the symplectic form applied to y and then x. Well, somewhere some choices got made about those conventions and someone made two opposite choices. And so a minus sign slipped into things.
Can you remind us what it means for the Lie bracket of two vector fields to be equal to 0? Like geometrically, what does that say?
So exactly what that says is that that their flows commute. So the Lie bracket of x and y is 0 if and only if their flows commute. So it's called phi x t and phi y of s is equal to doing the flows in the opposite order. So if you're sort of used to thinking about Lie algebras in connection with Lie groups, right? A Lie group is abelian. A connected Lie group is abelian if and only if its Lie algebra has trivial bracket, right? So
then the Lie group that we're thinking about here is these flows.
Yeah, right. That these flows generate an action of R2 as a Lie group. Right, that's what this expression tells you, that if I have x comma y in R2, there's sort of a unique operation I can assign to it by flowing with respect to one vector field corresponding to x and flowing with the other vector field corresponding to y.
Could you also think of it as like if you choose a point and you have two commuting vector fields, then the two flows will sweep out a surface, like a well-defined surface, passing through that point. Is there something wrong with that?
Yeah, right. That in order for that to happen, what you need is that the Lie bracket of the two vector fields is in the span of the vector fields.
Okay, so yeah, it's a weaker condition. I see.
Right, there's this Frobenius theorem in differential geometry,
Right,
which
right.
basically says that, you know, a set of vector fields kind of sweep out a nice foliation of your manifold into submanifolds if and only if
Closed
the
under.
span of those vector fields is closed under Lie bracket.
Yeah, got it. Mhm.
So right, the sort of thing that, you know, somehow should be that I think you're kind of getting at, right, is if you have an action by a non-abelian Lie group, then you have orbits by that Lie group, right? And that's kind of a nice foliation that's coming from the fact that, you know, every element in the tangent space, the identity in that Lie group gives you a vector field on the thing you're acting on. And those vector fields, their span is closed under taking Lie bracket, even though there might be lots of non-trivial Lie brackets between things in the Lie algebra. And one thing we calculated here is that the symplectic and Hamiltonian vector fields form Lie subalgebras, because we showed that the Lie bracket of two symplectic vector fields is Hamiltonian. So Canis de Silva writes these.
Wouldn't that imply even stronger that the Hamiltonian vector fields are an ideal?
Yes, in fact, even more than that, right? So I have symplectic vector fields, I have Hamiltonian vector fields. So yes, it's an ideal, and the quotient sim ham is H1 of M as an abelian Lie algebra. So it's sort of, it's even stronger in the sense that it's not just an ideal, it's an ideal where the quotient has trivial bracket.
Weird.
Maybe yet another way to say this is it's the derived sub-Lie algebra. All right, so, you know, I leave it to you to either look up or ask me or check yourself that vector fields are a Lie algebra under bracket. But maybe a slightly more surprising fact is that on any symplectic manifold, this operation of Poisson bracket makes the C infinity functions into a Lie algebra. And in fact, the map that sends a function to minus its Hamiltonian vector field is a Lie. Because of this annoying swapping things around in the bracket, I have to send F to minus the Hamiltonian vector field of F. And of course, I could have fixed this if I had somehow changed the definition of Hamiltonian vector field, right? And maybe I'll just mention. So what do we need to check for this? Well, bilinear, I think that's reasonably clear. So it's bilinear because omega bilinear, and because sending a function to its Hamiltonian vector field is a linear operation. I need to check that it's anti-symmetric. So it's anti-symmetric because omega is anti-symmetric. And then there's one last thing I have to check, which is the Jacobi identity. And that's a little bit trickier, but it's not too bad at the end of the day. And I believe that's covered in one of the exercises in Canis de Silva. You know, again, it sort of comes down to, you know, using these compound formulas and the fact that, you know, as always, it comes down to the fact that omega is closed, right? So in 1 and 2, I never used that omega was closed. So it's got to come up somewhere. And I'll just mention here, since I didn't write it out, this is a Lie algebra homomorphism from C infinity M R to the Hamiltonian vector fields. It's surjective by definition, right? So a Hamiltonian vector field is by definition one which is in the image of this map. And it's not injective. Rather, its kernel is equal to the locally constant functions. And I say locally constant functions because I didn't assume my manifold was connected. Right, so the important point here is that xh is equal to 0 by the non-degeneracy of the symplectic form if and only if dh is 0. And that's true if and only if you're locally constant. And of course, if my manifold were connected, I could just say constant, but I'm not assuming that. So I have to include the possibility that my manifold has many different components, in which case I could have totally different values on different components as long as it was constant on each component. All right, so this is pretty close to being an isomorphism. Its kernel is very small, but it's there, and it will cause us trouble later. So just wanted to kind of flag the existence of that kernel. There's a fancy word here I could use, which is central extension of Lie algebras. So a locally constant function has trivial Poisson bracket with anything else because its Hamiltonian vector field is 0. So it's central. It has trivial bracket with all other elements of the Lie algebra. So this is an interesting example of a central extension of Lie algebras. If you like to think about Lie algebras, and if not, then you can just ignore me for now, and we'll talk more about this later. Okay, running pretty low on time. We might just need to discuss some of this a little later next time, but let me say something. So a Hamiltonian system, that just means collect together the information of a symplectic manifold and a choice of function, which, you know, if I were in physics, I would think of as energy. So this is kind of a formalization of this kind of notion from classical mechanics of I have a phase space, It has a symplectic form that kind of carries all the information about distances I need, and then it has an energy function, and I get some time evolution out of that energy function. So we've done this calculation before of how does a function, observable, change over time, right? That's the Lie derivative of the function with respect to xh. That's the pairing of the Hamiltonian vector fields under the symplectic form. And that now has a fancy new name, the Poisson bracket of f and h. So if h is our Hamiltonian function, and then we think about the time evolution that comes from it, f is a conserved quantity. It's constant on the integral curves of, I wrote h, but I should have written xh, of xh, if and only if its Poisson bracket with h is 0. So functions whose Poisson brackets are 0 give me something very special. In this case, f is often called an integral of motion. This is one of these weird old-timey physics terms, but you'll definitely hear it used. And very locally, there should be lots of these. If I have a function, if my Hamiltonian function is not at a critical point, then I can actually choose Darboux coordinates where it's one of the Darboux coordinates. I think. If not, then I lied, but I think that should be possible. In which case, all of the other coordinates from the same set, so if this h is x1, then x2 and x3 and x4 and x5, etc., those are all going to commute with x1. So those are all integrals of motion locally. But it's much harder to find global functions that satisfy this. If you have a random function, random manifold, you shouldn't expect that. But in some cases, as often happens, right? You have something which, if you look totally generically, there's no way it's going to happen. But life isn't always generic. You might be interested in very special cases. Sometimes it is possible, and it's possible often enough that it deserves its own special name. We call a Hamiltonian system completely integrable if, so my symplectic manifold is dimension 2n. If I have n functions such that one of them is my Hamiltonian, they pairwise Poisson commute, and generically their one forms are linearly independent. So this last condition is necessary so that I'm not doing something dumb, like taking the same function n times, or taking two functions and then taking some linear combination of them. Right? It tells me sort of these functions are really genuinely different. So I'll note here, this is as many such functions as we could hope for. We can't hope to find n+1 completely integrable functions. I think I'm going to say this later, but let me just say it now. Right. If I have this situation where I have pairwise commuting, then that means that the symplectic form applied to fx, fi, x, fj is equal to 0. So the span of xf1 up through xfn has trivial symplectic form, so it's isotropic. But we did some symplectic linear algebra earlier on to show that means that the dimension of this span is less than or equal to n. So the biggest dimension it could be is half dimensional, in which case it's Lagrangian. All right, and that's because it's contained in its symplectic orthogonal, and its symplectic orthogonal has complementary dimension in 2. All right, so I can't have more than n of these that are linearly independent, because then I would have an isotropic subspace that was too big. N is the most I can have. So for example, if I have a free particle in Rn, yes, this is a somewhat silly example, but fair enough. My Hamiltonian is the square of the length of the momentum divided by 1/2m. Well, that Poisson commutes with the individual components of the momentum. Right? It commutes with P1, P2, P3 up to Pn. I shouldn't take all of those because the differential of the Hamiltonian is going to be in the subspace spanned by those guys. So I have to take all of those, but forget one of them. So I'm going to take all of them except for P1. That gives me an integrable system, which includes this Hamiltonian. And the fancy word for this is conservation of momentum. Cool. On the other hand, with the harmonic oscillator, right, I have this slightly more complicated Hamiltonian that involves the square of the length of the momentum and the square of the length of the position. My potential energy increases with the square of my distance from the origin. So I can construct an integrable system here, but it's a little weirder. I should take the Hamiltonian, and then I should take kind of the Hamiltonian in each set of coordinates. So you can check that if I look at 1/2m pi squared plus 1/2k qi squared. So that's sort of the energy in the coordinates corresponding to pi and qi, both kind of the potential energy coming from the distance from the origin and the kinetic energy from my velocity in that direction. That Poisson commutes with the whole energy function. So I'm writing the energy function as a sum of a bunch of terms that all Poisson commute with each other for kind of dumb reasons, right? You can check that the, should actually write this down. So one of the kind of key calculations here is that if I take the functions pi and qj, so that's equal to omega applied to x of pi, x of qj. We'll see how I do in terms of the signs, but it's all right either way. So if I compute the Hamiltonian vector field of pi, that means that I look at, keep kind of having to go up and do my calculation further up.
Sorry, Ben.
Yeah.
It's 2:30.
It is 2:30, you're right, shoot. That is a good point, but let me at least finish my calculation here. So this is I dd qi omega. So this is dd qi. And x qi, I'm going to get what you would expect, but with a minus sign, dd pi. And so this is -1. So if I'd written it in the other order, I would get, this is -1 times delta ij. So I get 0 if I and j are different. Then I get -1 if they're the same. So if I put them in the order again. IJ. Oh, it's after 2:30. All right, okay. So yeah, let me save any analysis of this situation for later, and we'll just note that here we have two not terribly difficult, but somewhat interesting illustrative examples of integrable systems. We'll talk a little bit more about the structure of integrable systems at the start of class next time. All right, any questions?
I had one.
Mm-hmm.
So just to clarify, the definition for completely integrable was dimension 2n, and we have k equals n integrals of motion.
Yes.
So if I remember correctly, there was a definition for super integrable, which was you have k greater than n independent integrals of motion. What is it that we lose there in that case? Like, what's the thing that we can't have in our definition here?
If you have more than that number of integrals of motion, then you can't be symplectic.
Okay, because I've got the Wikipedia page open here, and it says it's a symplectic manifold, and there's k greater than n independent integrals of motion.
I mean, that must be some different definition of independent.
Okay.
So let me.
Hold on, I'll put the link in the chat if anyone wants to. I was just trying to figure out what's the difference between what they're saying.
I will check. I mean, it's just. I mean, there must be something that's getting weakened here. I don't.
Yeah, that's kind of what my question was, because it talks about throughout the rest of the page how it generalizes theorems for completely integrable to super integrable. But
yeah, this is something I'll have to look at more carefully. There must be. Functional analysis and its applications. Like I don't have my proxy on. Anyways, are there any other questions?
Yeah, I have some, but does anybody want to go ahead of me? Because my questions are probably like weird.
I guess I sort of have one related to that previous one, if that's okay, unless we want to not.
No, I mean, I might just well say like, oh, I'm going to need to think about this, but.
I mean, I'm wondering, like, if you took a system that was like just r to the 2n with the Hamiltonian like h equals x1, wouldn't you have all of your other xi's, you know, Poisson commuting with the Hamiltonian as well as y2, y3 up to yn?
But they don't Poisson commute with each other.
Oh, okay, I see. Gotcha.
And I mean, I wonder if that somehow it's getting stuck in here. Let me actually look slightly more carefully at. Yeah, I mean, I suspect what's happening here, if you look at the definition, it's that there are more than n integrals of motion, but they don't all Poisson commute with each other. So it's instead like you're getting, you know, some interesting Poisson bracket between some of them. If you look at this condition 2, right, it says the Poisson bracket of integrals of motion reads blah blah blah. So you're sort of saying, okay, I'm willing to sacrifice the Poisson bracket between these integrals of motion being 0 in order to have more of them. and having some control over the Poisson bracket.
Gotcha.
And is the third condition the constant co-rank on the m equals 2n minus k thing, the reason why when k equals n, it gives us our definition for completely integrable?
Yeah, I am now. Oh, co-ranking. Yeah, exactly. Right. So it's sort of, this is as, it's saying that these functions Poisson commute with each other as much as is physically possible, or, as much as is possible, consistent with symplectic linear algebra, right? So what this is telling you is that when you take the Poisson bracket of two of these integrals of motion, you get a linear combination of the other ones. So it's essentially like a sub-Lie algebra. So it's like an action of a non-abelian Lie algebra instead of an abelian one. I guess the point is that that isn't constant, right? So if that matrix function S of ij were constant, then I would really be saying, like, you have a non-abelian Lie algebra acting, and that co-rank is like, is the dimension of the Lie algebra mod its annihilator or something. Mod its derived subalgebra. So yeah, this is like a theorem you could apply in the situation Henry mentioned, where you think about like, x1, think about all the other coordinate functions as except y1 as integrals of motion, and then you have to take into account the fact that they have non-trivial Poisson bracket with each other. And yeah, we'll talk next time about this stuff about tori. All right, any other questions?
I'll ask like one. I'm saving my other questions for later because I think you'll probably get to it. But like my one random question. Okay. How does this stuff interact with complex structures? Like, what if I had like if my Hamiltonian vector fields happen to be like 1-0 vector fields with respect to a with a compatible complex structure? Like, what would the does that have any implications for what I don't know. I don't actually have a precise question, to be honest. So
yeah,
just...
right, that's a little weird because remember, like a 1-0 vector field isn't a vector field. It's a complexified field.
Oh, right. It lives in the complexified.
Two vector fields.
Oh, yeah.
And so you're thinking about not a map of R, not a path.
Yeah, right.
But rather a map of C integrating, right?
Yeah.
So like you're going to get into complicated stuff about like, oh, well, do those two vector fields commute with each other?
Oh boy.
Yeah, I would. Probably that'll happen if the 9 house tensor vanishes or something. I don't know. But no, that shouldn't be it.
Yeah, I'll think about it.
Maybe it'll even. I don't know. But you. Yeah. Anyways, that's it's going to be complicated. I'm sure there is some nice thing to be said, but.
Okay. Gotcha.
And one kind of useful thing generalizing the stuff I talked about with Hugh is if we have a Kähler manifold J omega, right, then it's sort of worth thinking through like these definitions. So, so XH, right? This is the vector field such that well, yeah.
Are you writing? Because I can't see anything.
Oh, did I stop my share? Oh,
It's just frozen for some reason. Oh, no, I see it. You're moving now. Yeah.
yeah, I think it's, oh, no, that's not what I want to do. Yeah.
Now I
think
can
it's
see
maybe
it.
that I had like moved another window in front of
Yeah.
my computer. So the inner product of this guy with some one form alpha is the same as, yeah, I'm having trouble writing this. That's not what I mean. The symplectic form applied to XH and some vector field Y is equal to the pairing of Y with the H. Now, this is equal to, by definition, G XH J XH Y equals this guy, right? And the vector field that satisfies this property has a special name in Riemannian geometry. It's the gradient. So JXH equals the gradient. Oops. Of H with respect to the Kähler metric. So what you're going to get is like, yeah, I think kind of the natural thing to look at is like the holomorphic vector field, where kind of in one direction you sweep out this Hamiltonian path, and on the other hand, and the other guy, you do the gradient.
Like if you move along I, you'll get a gradient. If you move along like the real axis, you'll get a Hamiltonian type of
Yeah,
thing.
that's one way to say.
Yeah, I see. Weird. Okay, thanks.
So you should think of this Hamiltonian vector field as like some rotated version of the gradient.
Gotcha. Yeah, makes sense.
Somehow, like the symplectic form kind of tells you how to rotate. And that seems a little weird, but then you have to like kind of remember that gradient isn't a coordinate-free thing, right?
Right.
Gradient requires a metric. So really it's true if you have a compatible triple. Yeah, I guess I didn't actually use Kähler here because I didn't use that the complex structure was integrable. So this should actually work with any compatible almost complex structure.
Mm-hmm. Very cool.
All right, any other questions?